get started here. Welcome back. It's good to see about 2/3 of you. Maybe people will continue to trickle in. We left off on Tuesday with that design exercise, which was related to MP0 and how we could specialize the hardware to do one task reasonably well versus all sorts of tasks in a more general purpose way. Just to kind of finish up this discussion and why those points about parallelism and specialization came up, it was really to answer the question is, why are GPUs so fast? And part of the answer is that there isn't necessarily anything that clever going on architecturally. It is a reasonable evolution of the kind of things you would have already learned in prior courses about computer architecture. But these are some of the reasons why for GPU tasks there can be quite a bit of performance benefit over a CPU, over a general purpose processor, because of the parallelism both in terms of the functional units that can do things in parallel because of the algorithmic parallelism, as well as then the specialization of the underlying hardware as well. It turns out in most modern, really high-end architecture, microarchitecture, the actual amount of chip real estate for a floating point unit. In fact, this isn't even very good to scale anymore. That green box needs to be quite a bit smaller there. But the actual amount of real estate you need to do a floating point unit for our floating point multiply accumulate type operation we were talking about on Tuesday is actually quite small. And you can fit a whole bunch of them on chip. The real challenge isn't how do I get that much computation on chip. It's really from an architectural perspective, how do I feed data to all those architectural units? The rhetorical question here is that it's true. I think that computation is easier in the sense of designing a system to be able to do a lot of computation. It's actually an easier problem to solve than be able to do the communication challenge of how do I get data from some input source to all those different functional units, and how do I get the results back out in some meaningful sense. And GPUs don't exactly solve that problem. There's nothing magical there about being able to do communication more effectively, but that ties into a couple of the points here. If you have parallelism in your algorithm, then there's potentially less communication that's required. You can just send things and broadcast data out. You don't have to worry about the data dependencies and making sure that the output of one functional unit has to be directly connected to the input of another functional unit. Specialization can also help with that communication issue. If I have a really customized function unit that does multiply accumulate operation and some other custom kind of thing, there may be less data I have to pass around as well, because I don't have to go from the result of one more or less specialized unit to the input of another less specialized unit. I can keep all the data local there and not have to worry about where that data needs to go, at least in the interim, because I can keep it in that functional unit, do whatever arithmetic, whatever math is required of that functional unit, and then worry about the output side after that special logic has been done here. I showed this briefly on Tuesday, but if we were to compare one of these kind of die layout photos of a modern CPU to a modern GPU, there's certainly going to be some things in common. The first thing is you'll see in terms of any kind of regular structure here is at a much more coarse level here. So this is reasonably recent Comet Lake die photograph. This has got the integrated GPU as well, so we kind of ignored this part for now on the right-hand side of this die layout. And this stuff is what Intel would call their uncore stuff, so not computational stuff happening over here. You can see kind of the copy-paste of the transistor layout, hopefully, right? These are 8 cores, and you can see effectively there's 8 copies of that same design in the rough middle of this diagram here. But within those 8 cores, there's not a lot of regularity of the die photo of the transistor layout here. There's a lot of logic to handle a lot of different circumstances, to handle all the kind of things you learn about in earlier architecture course, just of course kind of cranked up to 11, right, in terms of handling multiple instruction streams, handling very advanced branch prediction, interfacing to different parts of the pipeline that may be clocked at different frequencies. So when we look at that computational density of the CPU versus the GPU, well, you can't easily lay out where all the control logic is. In some sense, it's all control logic, but we can at least look at the diagram and looking at some of those more regular-like structures. When we overlay onto a modern CPU, we actually see that in order to try to eke out more performance from general purpose workloads, a pretty decent percentage of this middle, 50% of the diagram here, while it does have a decent amount of computation in there as well, a lot of it's really just dedicated to cache. And that's really the other reason why our GPUs can potentially be faster. There aren't necessarily better architects working at NVIDIA than at Intel in any way, shape, or form. Their VLSI engineers are not more talented or something along those lines. They have roughly the same power and transistor budgets for the medium level, at least, of their respective designs here. The intentional design decisions on the CPU side is we're trying to handle all sorts of applications of varying amounts of parallelism associated with them and varying locality patterns as well. One design decision that winds up resulting in that determination is we do have this coarse-grained parallelism, but maybe that means 8 cores or 16-threaded architecture. And the rest of our chip real estate dedicated towards cache to try to eke out as much locality as possible to get as good of a cache hit rate before having to go off to relatively expensive off-chip memory. For the GPU design, a different set of determinations were made, that they're not as interested in single-threaded or even 4-threaded or 8-threaded or 16-threaded workloads. You can run a single-threaded workload on a GPU. It's kind of what we'll be doing for our GPUs we're building this semester. It's going to be quite slow on that GPU. The GPU is designed not also for then general purpose things. You can write general purpose code for your GPU, it's going to be quite slow. But for the type of applications we tend to want to be able to write for graphics rendering or for certain classes of GPU computational tasks, and for the type of parallelism we can generally get either out of the GPU rendering, graphics rendering application, or certain classes of computational tasks, the GPU has those resources available to be able to do as much computation essentially as you can throw at it. That's why GPUs are faster. That doesn't answer exactly architecturally what makes them entirely different, but at a top level, that's some of the differences in the design decisions that go into what a modern Intel 64-bit processor looks like versus what a modern NVIDIA GPU looks like. And the performance trends kind of reflect that. This is data that's actually quite hard to collect, and so it's a little bit dated here, this data. But in the GPU realm, historically, and still to some extent increasing even to this day, we've been able to see this, this compounded annual growth rate of generation to generation to generation or year to year to year of a pretty significant increase in performance from one gen to the next gen, beyond what just the density of transistors available on chip would have been able to predict, taking the same design and just increasing the size of it, beyond just what that Moore's Law would have been able to predict for it. It's kind of an interesting time in terms of transistor budgets, all the VLSI challenges, the fabrication challenges of those designs, but we're seeing even with somewhat of a leveling off of the amount of transistors available on a particular chip for a given process node, GPU performance is still tending to be able to increase, not necessarily in terms of having more computationally, but in terms of having more and more levels of specialization available here. This, again, as I mentioned, this data is a little bit hard to collect. It really is benchmark dependent, and people can be very opinionated about how one can collect that data. But this is one version of that data comparing floating point performance between various classes of CPU versus GPU, let's say roughly over the past 15 years. The left diagram here is so-called single precision performance, so 32-bit floating point performance. The right diagram is double precision or 64-bit floating point performance. What's interesting and not really able to be shown on a graph like this is one way that GPUs have been able to continue to increase performance in a way that CPUs have been less able to take advantage of is recognizing that we have these IEEE 754 floating point values. People familiar with single floats and double precision floats and doing C programming or other things. One of them is 32 bits wide, one of them is 64-bit wide. That's sufficient for now. There's different accuracy trade-offs and performance trade-offs of doing one versus the other. But one realization that GPU designers have been able to take advantage of is we have these standards. We probably have to support to some extent those standards, but for doing things like certain types of graphical rendering, and if you take another course, you'll learn doing certain types of machine learning, some inference applications, you really don't even need anywhere near 32 bits of single precision floating point performance. So we don't have an equivalent graph here for 16-bit floating point performance or 8-bit floating point performance. There's some people that look at 4-bit floating point performance because the CPU wouldn't have an equivalent graph for that. They don't have those units to be able to do 16, 8, and even smaller floating point performance. But even within the kind of standard should be supported by programs, single and double precision floating point performance. This is our x-axis, and the data points roughly referring to generational releases of CPUs and GPUs, with the solid lines here being your CPU architectures and your dashed lines being your GPU releases. And the y-axis is that teraflops number, which, it's kind of a theoretical number, which is if you manage to feed all of your floating point units with as much data as frequently as they could possibly consume them, how many floating point operations per second can one get out? And, well, first off, maybe the scale is not something that's necessarily that obvious to you. Those are just massive numbers. That's my first takeaway from those pictures there. When we look at something that's a 15 teraflop architecture, maybe because I'm older and have seen the advance of that technology, I would think, wow, that's a $300,000 high performance computing machine that takes up a room this size, and that's how I'm getting my 15 teraflops out. And it's a single chip now, so that growth has been quite impressive in terms of the amount of floating point operations that are possible on these modern architectures. So I think that's kind of one takeaway, with single precision being roughly double that of what's possible with double precision. It's not obvious looking at this, but these are at the different scales. So it's roughly 2x what you get for double precision. And then the other takeaway is that generally, and it is a little dependent on the benchmarking methodology, and it's not a fact that we can say a capital T truth that it's greater than, but at least for this class of benchmarking of teraflops of performance, your GPUs are significantly faster than your equivalent CPUs for that particular way of measuring performance. They certainly have more of those floating point units, significantly more of those floating point units. So if one had an application that could take advantage of all of those, then the potential performance is, and that's a pretty significant, apples to apples comparison there in terms of the cost of those relative devices, the amount of transistors in those devices, and the different design decisions leading to different floating point performances.
Why do some of the lines on the right in the double precision graph, why do some of them spike and come back down? Is it just that they're not supporting that as much anymore?
Right, and I was hinting at that, but didn't really get at that. So we learn about IEEE 754, single precision floats and double precision floats, and we're told use regular floats for some things, and if you really need accuracy, use double precision floating point 64-bit values. And for general purpose CPUs that are expected to handle from Python code to Fortran code, still that's what they're expected to support. And so I don't think you would see in too many of the solid lines a dip back down, and I don't think, at least not in this graph, there isn't in any of the solid lines. But for GPU, and we talk about why are they fast, and specialization being one of those reasons, there's been a recognition that while it may be necessary for functional correctness perspective to support IEEE 754 single and double precision floats, your code should still run and get you a correct result back out if you have those data types. For a large class of graphics rendering applications, and for, I would say, an increasingly important subclass of GPU compute applications, you don't need double precision. You don't need it at all. And they're recognizing, and we just can't have graphs showing it because there'd be no CPU equivalent, and it's a relatively recent thing as well. You maybe don't even need 32-bit floating point performance either. Just because it's a standard that people expect to have available doesn't mean it's necessary for a machine learning task or for a graphics rendering task. We can do kind of the numbers of that at some point if we're interested in doing that. Long story short, though, is that likely what had happened from, what is this purple one here, NVIDIA Titan. Titan is kind of like a marketing term for this. So they're best in class, workstation GPU. The design decision was made from one generation to the next that cranking up double precision performance maybe wasn't worth it. And they kind of reversed, versus going back, they kind of reversed that decision would be one way of looking at those data points, that certain HPC applications do need double precision, but there's a whole lot of other applications that really don't need it at all. And there's just fewer of those, and the chip real estate is spent on other specialized hardware, presumably also including things like 16-bit floating point. That's a little hand-wavy, but that's my understanding of what has transpired in the field with regard to that. The precision is an interesting discussion we will eventually have to have from the graphics rendering perspective. One way to think about the precision discussion is, we have all this math that we're going to be doing in hardware. Matrix vector multiplication to start with, right? To kind of transform vertices and move our triangles around on the screen. And determine when we do rasterization whether a point should be turned on or not on this particular location. But at the end of the day, and I don't want you to lose sight of that, we're doing math here. So abstractly, there's a correct answer for what the mathematical equations should result in. But ultimately, we have a pixel that's turning on or not on a screen, right? And it's in a location. And there's, 1900 X locations and 1080 Y locations. There's only so many locations. There's only 1 million locations or 2 million locations on the screen the pixel could possibly be located at. And likewise, for the pixel itself, there's only so many colors it could be. Some gradient of red, green, and blue, some combination thereof. There's only so many possible values that we can have for any given pixel. And that kind of fundamentally limits how accurate our math needs to be. Why do we need to know the location of this triangle in 64-bit double precision floating point value when ultimately it's either at location 7 or location 8, right? It's not going to be at location 7 and 1 millionth or something like that. So from a graphics rendering perspective, we can actually do the napkin math if we wanted to. There's definitely a limit in how much accuracy, how much precision we ultimately need. The pixel's either on or it's off, or it's either going to be at this location or it's at the one next to it. There are some rendering techniques that take sub-precision, sub-pixel accuracy into account. We don't do that very much this semester. So for our architecture that we'll start to learn about in MP1, we actually don't use floating point at all. We use what's referred to as fixed point. Now, depending on what courses you've taken, you've heard of fixed point or not before. We're a little ahead of ourselves, but how many of you have heard of fixed point representation? A couple of you. So it's maybe something in a couple classes, and it's okay. We will learn that, understanding that it's an integer representation that gives you a little bit of that fractional representation as well. That allows us to do integer math. It allows us to do the multiplication operator and the addition operator like you're doing for MP0, and to get generally good enough precision performance of our underlying GPU. We could have done floating point, it's just a lot more complicated. And so sticking with fixed point makes the hardware you design a lot easier to work with. Some of the software you'll be writing has to do conversions with regards to that. So if all of our software code is written with floating point values and our hardware is expecting these lower precision fixed point units to do the math, someone has to do that conversion. We tend to do that on the driver side. We tend to do that in software. Anyway, I appreciate the question. That's kind of what I'm seeing with these pictures here. I wouldn't take any of these particular data points as like truth, like, oh, it gets exactly 16 point whatever teraflops. But the trends, I think, are pretty clear there. And the gap is also pretty clear in terms of that type of performance. In terms of the bottlenecks, we don't really know necessarily, but ultimately any point of that graphics rendering pipeline could be the bottleneck. It's not necessarily any one particular place. Even though our code is always doing rendering, at least for the code that we're writing this semester, the nature of the render we're interested in may change, and that may impact where the potential bottleneck is going to be. And that's going to limit, the theory of this number from the reality of what you get in practice. Again, these numbers some of them are done via just datasheet calculations. Other times there are actual benchmarks that try to be as simplistic as possible to kind of maximize performance. But as we have these logical stages of our rendering pipeline, it really does depend what our application is doing, where our bottleneck is going to be, and what's going to limit our resulting performance here. That's true in all software. So, that's not unique to graphical rendering. It's much more explicit, I think, because we have such well-defined logical stages of what our hardware and software together are doing here. Again, there's that input side. There's the vertices and triangles that are coming in. That could be the bottleneck. I don't think for our applications it will be, but it could be the bottleneck. If you just have so many triangles coming in and that connection between the CPU and the GPU is limited in terms of how much throughput you have, that could be CPU or bus bound here. If the type of transformations you want to do in that geometry stage is either there's quite a lot of inputs or there's some complex processing you want to do there, that could be vertex bound, that could be geometry bound at that stage. Usually more likely is after we get our filled in triangles, we've done our rasterization, and now we want to do separate processing on each of those individual potential final pixels on our screen. Our bounds would be found there. We'll be pixel bound or fragment bottlenecked here. And that's just normally due to the fact that, for any given triangle, that's one triangle, you'll have many, many possible pixels as well, right? Our triangles, depending on the scene, will be larger than one particular pixel. So you'll have more fragments than you'll have triangles. So more work to do, more bandwidth to consume on that side versus on the input side of things. We will look into that for our applications and the hardware we design. But just like with MP0, our in the lab at least, our primary consideration is get it working. And if it's slow, it's still working. That's fine. And I always want us to remember that just because we're limited in terms of the design cycles. We're not trying to sell a product here. We're not trying to build a super fast one. But recognizing when that happened can also be useful when it comes time to debug things. Everything seems stuck. Well, maybe it's not stuck. Maybe you're trying to transfer a whole bunch of data and it's really just very slow here. And you actually have to change when you're trying to log and measure things to get the actual interesting stuff that's happening in runtime or in simulation in your design. That reminds me, and I should have said this at the beginning. I was waiting for Ben to show up. MP0 Demo Day is on Tuesday. You saw just a set of Google slide outlines for you to fill in as a group. I don't expect that putting together the slides to take you a decent amount of time. If you look at the MP0 submission, and I may not send another reminder about this, I try to be pretty explicit what I want you to submit for that. Of course, if you have any questions, just let me know, right? In terms of what should be going into the report, I try to even highlight in the PDF, please answer this question in the report, and please put this diagram in the report, and please answer this question in the report. And then when you go into Canvas and you do the submission, the rubric should explicitly say, got points for doing this, got points for doing this, et cetera, et cetera. I want to be able to grade it very quickly. And it's meant to be really clear in terms of here's what getting all your points is for the MP0 submission. So in terms of spending time, of course, get the stuff to work. Get a reasonably working design, get a result you're happy with, call it done. And then split up the work however you think is best, put the report together. For MP0, I don't think it'll take you that much time. It may start to take a little bit more for a couple of these other assignments coming up. But put together the report if you haven't been doing it as you've been going. Make that reasonably easy for me to review and for me to grade. That's in both of our mutual benefits. So just make it that you've answered the questions I've posed and you get the right, you get the points for answering those questions. And then for the presentation, you can probably just pull from that report quite quickly. The figures that were going into the report, the kind of questions you already had to answer for the report can be the layout for that presentation on Tuesday. We actually have enough time. There's only 4 groups. We'll spend, let's say 12 minutes should be sufficient. I don't want you to have to stand up here and talk for 20 minutes about your MP0 design. I'll try to keep it timely, and we'll just kind of discuss and see what different teams did, what was in common across the different designs, what was different between the different designs, and that'll be just kind of how we spend most of Tuesday's class. And then we'll continue lecture after that demo part is done on that Tuesday. So that is this upcoming Tuesday. So the next time we meet together, it's an easy day for me. I'll be sitting where you're sitting. Your groups will be coming up one by one and just kind of talking about their projects. Fill out those slides. I'll have those slides open here, and we'll just walk through them together. And any questions about that MP0 submission, demo day, anything like that? You guys are very mellow today. No one's actively sleeping, so I appreciate that, but just very mellow. So that's fine. We'll see how it goes. It's meant to be informal. You're not getting graded on the quality of the presentation on Tuesday. I think you want to give a reasonably good presentation so people can understand what your design was about, but it's not part of the rubric itself that you gave a nice presentation. So it's just meant to be a discussion as a group, kind of a post-mortem of MP0, what worked, what didn't work, what problems you faced, and how you overcame them. For MP0, the presentations might look kind of similar to each other, but I guarantee you that will not be the case. Once we start to make more progress on the labs, the designs between teams will start to diverge quite a bit. And so you'll start to, see what problems were solved by other teams, how they handled things differently, what worked, what didn't work. It's supposed to be fun. That's my hope. But we'll find out on Tuesday if it's fun or not for the class. I wanted to show what GPU programming looks like for modern day systems. Reflecting on this slide and this example I was going to bring up, it's not that great of an example. It's just an example of a potentially parallel algorithm. So the Kahn summation algorithm is just summing up a vector. So it is a vector sum application. And while I talk about this, let me get the connection to the computer up and running. I never actually connected. It takes a vector of number and adds them up, or does some sort of summation. In hardware, we sometimes refer to that as a reduction circuit. In software, we can think of it as like a vector sum. And it does that summation. And this algorithm is a little bit different than just a loop that just adds up all the values. It also recognizes that as you're adding a potentially very large number of values, and if they're floating point values, there can sometimes be issues with the precision of that addition. That if you add a really small value to a really large value, because you've been summing up all these numbers, you may wind up losing some precision in the end result. The large value may wind up kind of overwhelming the small amount of change that is in that smaller value there. And we're talking, millions of values that you're adding up of floating point values here. So this algorithm isn't something we need to know in terms of necessary for this course. It is just an example of an algorithm for which a parallel implementation may be possible. That, yes, we can write a scalar version of the code that is just a single for loop here, but we can recognize that, well, as we're adding up this vector, and it only makes sense if it's a very large vector of values, we can parallelize that as well. If we have 8 processors, we can give each of them 1/8 of the vector, and then once they've done their job, then combine those results together at the very end. If we have 10,000 processors, we can divide it up into 10,000 and give each of them their individual task there. So the algorithm in terms of doing the error correction isn't necessarily that relevant. Just an example of something that one can do via parallel programming on a GPU. The examples I have and that we'll be sharing with you on and off again this semester as we learn about it, these are written in CUDA. We'll talk about what that means in more detail eventually. It's written as part of the CUDA SDK, the examples that NVIDIA provides. That's both good and bad. It's good in that they're tested, documented examples, so that's a good thing. It's not just random code from the internet. It's bad in that they tend to be written in this kind of overly exhaustive kind of style. The files are, a couple thousand lines when some of them could really just be a few dozen lines. So there's a lot of boilerplate code to make it as general as possible. So I think they're not great from that perspective. You have to read a lot more code than I would normally want you to do. But they're not a bad starting point. As we learn about GPU computing, to learn what it looks like to have CUDA code to code that would map to a NVIDIA GPU, these examples are as good as any that you would find out there. This is some slightly templated C++ code here. This one is the single-threaded version. It's called reduced CPU. It's implementing that Kahn algorithm for summation of a set of floating point values. Or it's templated values, but it would probably make sense if it's a floating point value here. And it's basically what was on that slide here. That is just C++ code. The actual code, I'm going to have to scroll down, I think, a decent amount to find it, that is going to tell, and let me also mention that this is C++ code. You compile it with a regular compiler. You use NVIDIA's compiler. You execute this code on the workstation, on your CPU, running Linux or what have you. This is software code. That's all that's happening here. As part of the framework and drivers and libraries that NVIDIA provides, they also provide some things that aren't really, strictly speaking, see if I can find it here even though, strictly speaking, C++ code. They are additions to what is otherwise just kind of standard C++. There's a lot to scroll through to find what I'm trying to find here. Well, this will be quick if I can't find it. Just give me a second. Might be in that other file there. There are things like copying, allocating memory, copying data over. Here's the actual call here. It's not super obvious and interesting what's going on here, but this call is saying, hey, I'm on the GPU. I want you to actually call code on the GPU and to run what kind of looks like a function call here, but run it in such a way that you're specifying, I want to launch it not just as a single threaded function, a single for loop, but parallelly kind of distributed across all those different little green boxes that were on the diagram from Tuesday, all the different little CUDA cores, the streaming processors that are available there. You then have, as a programmer, a slightly different task, which is writing the code that is going to be resident on the GPU as well. This is all code that's running on the CPU. On the GPU, you have code, and again, it's written in that kind of SDK kind of fashion here. And let's see if I can find reduce 0 would be fine. Let's see if I find that one. There's multiple different versions here. This is fine. This would be an example. This is code that you can call this a CUDA kernel is the term that we will use. And this is the code that's actually then going to be running on the GPU. And it's a different style of programming. If you've done parallel programming before, if you've done MPI or OpenMP or other things, there you're really being very explicit with how you're parallelizing the task, how you're potentially copying data around in the system, and getting some potential benefit from that parallelism. For the CUDA style, you're actually writing what still appears to be kind of single-threaded code here. There's a lot of syntax I don't expect you to know at all with regards to this because it is very CUDA-specific stuff we have not covered at all. But I think if you squint at it, it is kind of just a for loop. It is just kind of single-threaded C code going on here, adding up a bunch of values based on what we have here. The magic of it, or the interesting aspect of it, is what is the input to those functions, those CUDA kernels, tends to be just two things. Tends to be just pointers to our input and output data we're interested in. So you're passing a pointer versus just the actual data itself. And it also has assigned to it then as an input some sort of ID or some sort of index that lets the code as it's executing know, I am this particular thread. I am thread 3000 out of 50,000. And then the code should be written with that index, that ID in mind. And one of the first things you tend to see in any CUDA kernel is what I call kind of thread bookkeeping. Keeping track of where I am, how amongst all the threads, which one is this particular one, and executing the task based on what that particular value is. So this code, this is modern GPU code here. This code released in the last year and a half. This code is written as if it's from a single thread's perspective, but then each thread is going to be doing something slightly differently depending on which thread number it winds up being. So that's the model that we have to adhere to. We run this code on as many threads as is reasonable for the application. Each of them are doing a different piece of the task to get an end result back here. It's a little hard to see exactly where that's happening. It's copying data into a local cache, basically a software managed cache here. It's doing the actual reduction operation. And then if I'm thread 0, I want to actually write the result back out, is basically what's happening in that code here. Otherwise, yes, it is different than the CPU version of the code that was on the previous tab there. It's not that different. It's doing the same math. We're just saying, now do this math, do your own little particular piece of the math, and then we'll collect all the results when we're back done here. We can run it. It worked. I mean, I don't know, reduction application isn't all that interesting in terms of the end result of what it's doing here. Gives you some idea of what kind of performance is possible. That would be reduction throughput, which is basically how much of an array can you reduce to a single value. So that can be measured in bytes per second. So that's a pretty decent amount of throughput for taking a large amount of data and kind of reducing it down to a single value. In terms of showing off the power of the GPU we're connected to here, which is a Titan X GPU, it's a reasonably decent GPU. That one's not very good. We can do some sort of graphical things and show, it's capable of all the kind of things I think you're hoping to be able to learn in a class like this. This is a particle simulation here, where graphically it's not doing anything that interesting, but there's a lot of behind-the-scenes calculation for each of those individual particles they have a particular life associated with it, and they correspond to a different pixel. Ultimately, based on that calculation, they interact with each other, they potentially collide with each other. I can probably, there's an OpenGL application, I can probably move the camera around and things like that as well. It's casting a shadow and doing things like that also. Anyway, I want to just show at this point still what our GPUs are capable of and give this high-level argument about, it's kind of mesmerizing, isn't it? This high-level argument about why our GPUs can be potentially fast. This code view is definitely part of the argument. I understand we're not there yet in terms of fully understanding that code and being able to write that kind of code ourselves. That's one of our learning outcomes of this course, to be able to get to that point this semester. The interesting aspect, though, is as we get this continued scaling of graphics technology, of our amount of computation, of the specialization of our computation, of the parallelization possible, we're still really not there yet. I mean, it's a debatable thing in terms of kind of real-time interactive computer graphics of reasonable, acceptable fidelity. But what has happened many times throughout history is that there was a certain fidelity of what was possible in real time and a certain graphical fidelity of what was possible via just kind of overnight rendering or 1 hour per frame or something along those lines. From Pixar to real-time kind of rendering differences, there's always been that gap. But what has happened many, many times now across many technology generations is what was only possible via this kind of 1 hour per frame batch mode of rendering became something that eventually was something that we could do 60 times per second. And that transition from what was batch to what was interactive has happened many times now and will continue to happen. We still probably have a long way to go in terms of what we would consider the amount of complexity required to kind of render something that looks truly realistic beyond just the artistic challenges and limitations there. From a technology perspective, we still have a long way to go. So it's still relevant in the sense that as these improvements have continued to be made, we're not done yet. And so there's still need to, even though we have these devices, we have this much computation, these teraflop numbers, multi-gigabyte numbers available to us, it's still not enough. And so I think that makes it still kind of a relevant topic to kind of still study. We, in this class, we learn kind of this evolution of graphics hardware. We build a reasonably, what do we call it, a Gen 4 device by the end of this semester. And we learn what is kind of modern beyond that as well. But I don't want you to come away from this class thinking that it's kind of a solved problem, that there's no further need to kind of innovate in the graphics hardware side of things, because what was, possible only via multiple machines taking quite a bit of time to render, over time became something that we could do in real time. That evolution continues to happen. So anything that is Pixar quality today could hopefully become real-time rendering possible tomorrow. That still requires innovation from a computational perspective. There's still quite a bit of need for you in industry to be able to design the next generation of GPUs. And finally, I like to do this with every class, and so it would have been preferable if we'd gotten to this on Tuesday. But for each class, at least that I teach, and certainly ones that kind of span the hardware-software divide, I just want to talk about where we are most fluent in this class, where I kind of hope you already are as a student, although knowing that we're all kind of developing our skill set, and where you'll definitely develop more this class. This is one view of kind of the general hardware-software stack. I'm more of a hardware guy, so I kind of focus on more details there. You could subdivide the software stack quite a bit more as well if that was your passion. In terms of what I think you already should have some exposure coming into this class. If you came to me and said, I have no idea how to do C programming, hopefully I put you on a team where you can balance that. Nobody told me they didn't know how to do C programming. I kind of expect that. Looking at what I've seen in the lab so far, and even some of the discussions we've had in class, my expectation is you had some digital design knowledge of what it means to build a pipeline, what it means to interface with memory, or to build a finite state machine. And I think it's okay, just based on some discussions and some monitoring of what's been going on in the lab. It's possible collectively as a class we're not necessarily super strong there. It really depends on what classes you took, what projects you've taken. If need be, we can spend more time on finite state machine design in VHDL and Verilog. It's a self-contained topic. It's an hour. There's you're not supposed to be creative with it. There's a way you're supposed to do it, and you're supposed to follow that design pattern. You'll be doing a decent amount of that this semester, so my expectation is you kind of know how to do that. As a team, hopefully one of you knows how to do it, and the rest of you can kind of learn how to do it. It's easy for me to say it's not hard. Maybe it's hard, but it's a recipe. You have to do it a very specific way, or you'll get unexpected results. And I do expect you to be able to do that. What you will then be continuing to learn this semester would be kind of the remainder of the concepts and tools that we'll be covering here. We spend a decent amount of time on-chip communication in this class, probably as much, if not more, than like an embedded system, than like a 488 class would have to cover. The platform 488 solves a lot of those problems for you in a good way, so you don't have to think as deeply as about them. We have to solve them ourselves. We have to deal with on-chip communication. This next topic, which was, I said, the background topic of what we need to cover, does talk about things like bus arbitration and the like. We have to be aware of the underlying I/O interface, but we don't design for it, so that's something you will learn more about. And certainly, if you haven't come into this class already knowing a little bit about graphics programming, we'll do our boot camp with OpenGL. We will all get to the same place in terms of understanding OpenGL programming. We can't really fake that this semester. We have to be very well aware of how our C program calls OpenGL functions, how those OpenGL calls then have to correspond to some sort of directives on the hardware side, and then consequently how our hardware is going to be designed to look for those directives, those configuration values, those commands, and to do what is expected of them for those API calls. So we do need to spend some time, spend a couple weeks learning OpenGL in this class, just enough to be able to do what we want to do in this class. If you find that that's your passion, I think you'll find a lot to like about this class because the type of things we do in terms of demoing for the labs is here's one triangle. Okay, now here's 50 triangles. Now here's a purple triangle. Very basic stuff for testing purposes. If you find that you're really enjoying doing more creative things with OpenGL, you should be able to show that that stuff still works, on your team's hardware, and so it'll make for really cool demos as well. Any questions about this graph, this view of like the kind of things I'm expecting of you this semester? And I highlighted things I was hoping you already had, and then the things I think we'll be learning this semester. How are we doing for time here? We got plenty of time. There's a bit of a context switch, so take a minute, stretch, breathe, or something like that. That's fine. Got to our introductory material. That's all that was. So my goal with that previous material is just to kind of inspire is not the right word, to get you interested in the topic even more than maybe you already were by signing up for this class. This topic is a bit of a grab bag of just underlying technologies that I just realized in looking at further material, I kind of assume you know. And so some of the stuff you may know and some of the stuff you may not. And so we're just going to cover it reasonably well. Let's get through raster graphics and memory and display hardware today. And then after demo day on Tuesday, we'll finish up this topic either Tuesday or next Thursday. So it's a little disconnected is all I'm going to say. This is just system stuff that we need to know to be able to do the things and understand the underlying things for the labs and just conceptually in this class as well. So here's a big picture that I already kind of mentioned, but I think it's good to have in your mind in terms of the very high level architecture of a graphic system. There's a couple things here that I think are important. I had mentioned this already last week, but just to reiterate, there's generally always a CPU in the system somewhere. There is a processor, if you want to call it just that, in the system somewhere, running your operating system, running your application code. It's there. It is going to be connected via some mechanism, we can call it a system bus for want of a better word right now, to, in a graphic system, an underlying display processor, or we can call that our GPU. We can use the terms interchangeably here. The idea of having that is that it's a coprocessor. What is the point of a coprocessor, right? It's to offload things that the CPU could technically do itself. It's a general purpose processor, can do anything itself, but it's not dedicated to that task. We offload certain tasks to a coprocessor to specialize in that task, to be better at doing that task than what our CPU would be able to do. That's all a graphics processor or a display processor is. It is a coprocessor dedicated towards graphics tasks. The CPU still has that connection via that system bus. It is the one basically telling the GPU what to do. Render this scene. I'm going to set up the scene. I'm going to load all the textures and geometry and things like that. I'm going to send it over and say, render this scene. The GPU, what it necessarily has, really depends on what type of technology we're talking about. But generally, for the type of systems we're interested in, which is not all systems, but the type of systems we're interested in, it's going to have some sort of memory associated with it as well. Whether it is a physically separated thing from our general system memory or not is an implementation detail, but at least logically we can think of the CPU having access to some system memory, the GPU then having access to its own GPU memory. Again, whether it's a physical memory or not doesn't really necessarily matter. It has its own memory region, its own address space. As part of that memory, some aspect of it, whether logically or physically, is going to be dedicated to holding that frame buffer. That's going to be holding the current image I want to next be displayed on the screen. We talked about it a little bit last week, but that's the same concept we talked about then. It's no different than that. We have a certain region of memory storing our pixels. Given the resolution, given the amount of depth per pixel, it's going to be that size of memory. The display processor's job is to fill up that memory as quickly as possible to get the images back out. What we hadn't talked about yet is there has to be another aspect of that. If this is on the writing side, or the right operation of filling up that frame buffer, there has to be another piece of usually dedicated hardware to do the read side of that, to read from the frame buffer for what pixels were meant to be the next frame in memory and to drive a display. Call that the video controller, ultimately connected to whatever monitor you may have here. You don't always need that. Sometimes we have rendering systems that only render to files and only render to some static frames. But if we're doing a real-time interactive system here, we have usually a frame buffer and then we have some separate video controller that is connecting to the monitor. So I use the term rasterization, and I mentioned briefly it has to do with the base word of raster and raster scanning. And another word for that is just this kind of linear zigzagging scan here. So if we have a raster scan system, which most all modern graphics hardware is assuming underneath the underlying assumptions of the video controller, we have a display. And that display gets redrawn not actually literally all at once, at least from a control perspective, it's getting redrawn on a line-by-line basis. That is our so-called raster scan. In rasterization, raster graphics are related to that word, but here the raster scan is the pattern by which we are up. It's probably backwards from your perspective. Maybe it'll look good on the video. That left to right, up to down pattern of which we are displaying the values that we have here. Redrawing line by line, a fixed number of times per second. Originally invented because this was kind of the only way that the technology was able to keep up with being able to fill a screen. It is, to some extent, a disadvantage now in that via standardization, we are kind of supporting things that were meant for kind of old school physical ways of updating a screen that aren't as relevant today. We'll talk about the VGA standard in just a minute here. So at a very high level, our video hardware, our display hardware is reading from memory. So it's providing an address, doing a read request of an address in memory, and at some point there's then going to be an element of that frame buffer, a location in memory that corresponds to what that pixel should be on the screen. If this is really obvious to you, that's totally fine, but this is necessary that we get this, otherwise MP1 will definitely not make any sense for us. Region of memory, and at the very least there's one bit in that memory. There could be more. At the very least there's one bit to correspond to should that location in memory be turned on or off. That location in the screen be turned on or off. We visualize the frame buffer as being this two-dimensional thing, but we know memory is probably this linear array of storage, but it's a two-dimensional logical representation of XY locations in our frame buffer corresponding to XY locations in our screen. So as part of that raster scan, there's that conversion. We read these consecutive addresses in memory, we read out what digital ones and zeros are stored corresponding to each individual pixels, and then at some point there's ultimately still at some point there's some digital to analog conversion there. Whether it happens at this point or at the final kind of display side, at some point there is some conversion, a RAM deck or other conversion circuit that says, given this value that's stored in the frame buffer, I want that image, that location in the raster to be turned on or off. So if this was just a binary display of just on or off, that's all you would have to store. It's just 1 bit per pixel in your frame buffer here. What's not shown here is, there's some DMA type operation where we are loading in these blocks at a time, and then we have some physical display conversion that has to happen there as well. So we have this concept of the display's resolution. That's the number of lines. That is our vertical resolution. We have the number of pixels per scan line. That's our horizontal resolution. And then finally, we have how many bits per pixel we actually want to store. We did a little bit of this napkin math last week for different resolution, different types of display resolutions, roughly how much frame buffer storage would be required for that. The math that we did last week was about throughput, but this is part of the calculation. If I have a 640 by 480, I need 640 times 480 pixels. Then if each of those pixels is 2 bytes or 16 bits here, that's how many kilobytes I need to store that particular frame buffer. It actually ramps up quite quickly, right, in terms of as we grow both the X and the Y dimension, the horizontal and the vertical resolution here, and the amount of bits per pixel, we do wind up having a reasonably high amount of storage for your 4K and your 8K systems here. And here are just some kind of physical real-world equivalences. This isn't literal, but if we have a laser printed page, the fidelity of that printing is measured in dots per inch, and that is effectively the same as like a resolution as well. So you can roughly say, to store each individual dot, here's how much storage you would have. For truly kind of analog domains like analog film, 35 millimeter film, it's a bit rough in terms of the conversion there, but you can get a rough conversion of what that would correspond to when fully digitized and having a raster scan equivalent to that. So in terms of now, what does it mean in practice to have now not just a single 1 or 0, just this binary frame buffer? What does it then mean to have color? Well, it depends on how many bits per pixel we're going to have here. Generally, for the kind of systems we're interested in, we would have an RGB color system where there's a certain amount of storage for the red component, a certain amount for the green, and a certain amount for the blue. At its very minimal amount, then you'd have a 3-bit frame buffer, where, again, this is kind of a logical arrangement showing kind of a 3-dimensional arrangement of your frame buffer, but ultimately for each XY location, you would have more than 1 bit you would be reading at a given time. In this case, at least 3 bits for 1 bit of red, 1 bit of green, 1 bit of blue. And then you would effectively have some combination of that red, green, and blue to get the resulting color that would show on the screen. We will talk next week a very small amount about color theory. It is a very fun topic. We just can't spend too much time on it. For now, you can make the colors you're interested by combining red, green, and blue. If you ever worked on color codes or used a paint application where you're trying to find the right color, it gets encoded as a certain amount of red, a certain amount of green, and a certain amount of blue. Our video display controller takes that same concept into account when determining what the resulting color is going to be. We also can have this concept of indexed colors, where you have an intermediate table. It's called a color table, which can be used to fetch the colors from that table as kind of an intermediate step to driving the end result here. The idea being that you can potentially save quite a bit on memory storage here and still have a large number of colors. Your old video game systems, very commonly had to rely on this technique. If you ever heard of like a color palette, that's what it's referring to. You would have this intermediate storage of a reasonably higher fidelity, but with a limited number of possible values that you could have at any one given time. Walking through what I'm talking about here in terms of the layout, you would have your n-bit frame buffer. The idea being that n is not that large. Maybe n is 8, just to give an example, so that your system could support 256 different colors. If you have 8-bit values, that's the unique number of things you can encode with that 8-bit. And then if you have this color palette or this color index or this color table here, you would then use that value that got read not to directly drive the display, but instead to actually look up into a larger width of table that would potentially only have 256 entries in it, or in this diagram, 2 to the n entries in it, which would be of a different potential width. So 8 bits to store in the actual frame buffer, So for your resolution, you're storing 8 bits per value. Then you take the value and you use it as a lookup into this larger table that says, okay, here's a wider range of colors we can represent. Maybe it's 16-bit color, but there's only 256 different colors that could be stored in that given table at any given time. It's an extra kind of lookup step that you would have here from n-bit lookup to now maybe an m-bit lookup, where m divided by 3 is for the red, green, and blue components themselves. You may even want to do this for a 24-bit color system, where 24 bits is considered sufficient. Any thoughts? Why would you even want to potentially do that? In fact, you certainly can store images using index color today. You don't have to directly represent the color. Why would you want to even do that, even if you had enough storage here? And we'll let you guys think about that. You don't have to answer it right now. There's reasons, either artistically, in terms of bandwidth savings, there's reasons you would maybe still want to have indexed color, even if you don't technically need to. Even if you had enough storage for m bits here and you could skip this step, there's still potentially some value in having that indirection step there for representing the color. That's a single frame buffer, ignoring the color table, a single frame buffer to store the result. We very often have systems that are either double or triple buffered, including the system that we are going to be building starting in MP1. Because what happens when you write to the frame buffer while it is currently being displayed? Wish I had a good demo for this, but I don't. But conceptually, we can work our way through it. Right, this diagram doesn't really show up, but if we go all the way back here, there's a write operation happening in the frame buffer, while in parallel, there's a read operation happening. Right? Our graphics processor, based on whatever calls that it was told to execute, is updating that frame buffer. This pixel at location 47 should be red. 48 should be green. 49 should be blue. In parallel, simultaneously, while that is happening, that is the write operations into that buffer. In parallel, simultaneously, while that is happening, the video controller is reading from that region of memory. I need to grab pixel 47. I need to grab pixel 48 because I need to connect it to display it on my monitor. I need to convert it to some analog signal at the end of the day here. What happens when those two things, they do happen simultaneously by design. The writing to the frame buffer and the reading to the frame buffer are happening simultaneously. We want to write to our frame buffer, let's say 60 times per second. We want to read from our frame buffer 60 times per second to be able to actually drive our output display here. What happens when they're happening simultaneously? I want to write to the same, let's say same location in the frame buffer at the same time it's being read out. What would happen? Let's say the previous frame, I drew a picture of a dog. We could do red triangle, green triangle, but let's say it's a picture of a dog, the previous frame. I'm in the process of displaying that dog on the screen. Next frame I'm going to be displaying a picture of a cat. Without any double buffering, which I'll talk about in just a moment here, in the single buffered version of the same, what would be displayed on our screen potentially? Potentially a half dog, half cat, monstrous, hybrid animal here. This idea of scan conversion and what's the term here? It's not flickering. We'll call it flickering for now. Is a common concern that you're trying to update your screen while you're also trying to update your frame buffer while you're also trying to display what is in your frame buffer. And there's really no mechanism with a single buffer unless you have some very clever handshaking and timing and you somehow guarantee that it's never happening simultaneously. There's really no guarantee that that won't happen, that as you are both updating the frame, you're also not half in the process of displaying that current frame. Now, in practice, it's never that bad. You never want to switch between cat and dog at 60 frames. It's not going to look good anyway, right? We're going to have trouble seeing that. But we have our triangle moving on the frame, and our triangle is moving from location to location. And what you will wind up then having is a triangle that's like halfway moved to that next location, 1 pixel over. You'll see it's not flickering. It'll come to me what the term is called. That kind of overscan effect of seeing the previous frame in part and part of the current frame simultaneously if you just had a single region of memory, a single buffer for it. A much more common approach. Those are both problems we have to worry about. Say it again? Screen tearing, thank you. Okay, geez, okay, got it. Or flickering is fine too. Yes, okay, thank you. If we have two buffers here, this double buffering approach, and you will learn about triple buffering as well, that is to some extent a solution for that problem. Logically, it's implemented as just a mux, a logical mux between our buffers, where we just separate which buffer is the write buffer from which buffer is the read buffer at any given time, to avoid the screen tearing, flickering kind of issue here. The way this is shown is kind of as a switch here, is that currently this buffer is the one that's driving the display. And in software, in our graphics logic that we're executing right now, this buffer is the one that's getting updated. So this becomes a write-only buffer, this one becomes a read-only buffer, and only after we've finished writing the frame generally is when we would do this, but when they're both finished effectively, do we then flip the switch. And now the one that was the write-only buffer becomes the read-only buffer, the one that was the read-only buffer becomes the write-only buffer. This switch moves to now start reading from this location here. That is the double buffering solution. A physical switch is a nice way logically to think about it. In practice, we don't need to physically do that switch. It could just be different logical regions in memory. You can think of it as base addresses, and we're switching which base address we're either writing to or reading from, basically just toggling it from frame to frame. And that does generally kind of prevent that problem from occurring. In terms of the underlying memory technology, let's leave things here for now. This is a good stopping point. We'll talk about DRAM, we'll talk about bandwidth, we will talk about what implications that has for our particular platform as well, and we'll talk about representing color in our platform and in other platforms. We will do that after demo day on Tuesday, so please come prepared. Again, it doesn't take you long to put those slides together, but don't wait until 9:15 that morning on Tuesday. Just get it done so I can review it before class as well. And I would like everyone to be here on Tuesday. Let your class project partners know to come here as well. And you can stand up here and talk about your design for about 12 minutes each. Okay? Good luck. Work hard this weekend. I'll see everyone on Tuesday.